Okay, so we'll proceed on orthogonal component or independent variable. Okay, so we started calculus or vector discussion with calculating partial derivative along x-axis, y-axis, and then partial derivative of any graph along a particular vector. So partial derivative of a graph along x-axis, I vector, j vector, k vector, or along any vector. I mean, this is what we have been kind of doing. Now, then we say that it is too difficult. Means we have to understand so many things when we go for a kind of partial derivative. So then we have to understand gradient and then so many. So then we landed up in that. Let's go for chain rule. If I want dz by du, then d fxy by dx, dx by du plus dfxy by dy by du. So rather than calculating so many things, better to calculate, better to go with the kind of chain rule. Okay, so that is the something that is next one. Now, so after kind of calculating the partial derivative gradient and so many complex things, we proceeded to we proceeded to chain rule. Okay, so now era of chain rule we are crossing. So all these are research based that we are doing. Repeatedly, I am saying that you won't find in any book. So we are going to file as many disclosures, at least whatever the video count we are carrying. So that is the idea. So now from the chain rule, we'll move to component way. So if I have a vector, then vector can be vector is nothing but set of three orthogonal components: x-axis, y-axis, and z-axis. That we have seen. Orthogonal component, independent variable, what it is. First, we understand the concept of independent variable. Okay, like I have a set of wires. Okay, so one is blue. Okay, and one is reddish, brownish, and uh, and one is green. So I have three: red, green, and blue set of wires. So based upon the color, I can say they are orthogonal. They are orthogonal to each other. Okay, based upon the color. That's it. Now let's see what is independence in the event. I have two coins. Okay, so this is in India. This is 10 rupee coin. This is not simple coin. This is 10 rupee coin, and this is 20 rupee coin. Okay, so there is a coin. I believe it can be shown. Okay, so this is a 20 rupee coin, and this is 10 rupee coin. So 10 rupee coin and 20 rupee coin. So there are two coins. Now they are in my hand. Now I am tossing it up. Now tell me that what is the chance that both are, one is head and one is head? Or I would rephrase. Now in left hand I have 20 rupees coin. In right hand I have 10 rupees coin. Consider they are just coin. They have head and tail. Now if this coin is head, if this coin is head, then what is the chance that this coin is head? If two coin, if I toss, then what is the relationship between one occurring, another's another? So this coin whatever we get, how it is dependent upon the occurring of head and tail on this coin. They are not dependent. This is independence in the chance, in the event. If I toss, okay, so if I toss two coin, then coming head and tail on one coin, coming head and tail on other coin, they're completely independent to it. They're not dependent. So if I say what is chance, then it will be head and head. Then what is the chance that it is head here? 1 by 2. What is the chance that it is head here? 1 by 2. So 1 by 2 into 1 by 2, 1 by 4. Or if we go with a sample space, then this is head, then this is head, one chance. Head, then tail, one chance. Means one item in sample space. Now tail, head, tail, tail. So there are four possibilities. Head, 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 tail, head, tail. Out of which I want head, head, then 1 by 4. Or if I go with the independence in the event independence, then event coming head here is 1 by 2, coming head here is 1 by 2. So though both are independent to each other, then 1 by 2 into 1 by 2, that is 1 by 2. This is independent. Both are independent to each other. Head comes on this coin, head comes on this coin. They are not related to each other. This is independent. Now, this is 20 rupee coin and I toss it up. Okay? One time. Again I toss it up. Second time. What is the probability that I get head and head? Same. First time if I toss, whatever I get. Second time if I toss, whatever, they are not related to each other. This is orthogonal. Both events are orthogonal to each other. They are not correlated. Okay, like if if I if if I get, okay, if I get head, then I'll toss another coin. Now this is 20 rupee coin. I'm tossing it up. If I get head, then I'll try tossing this coin. If I don't get head, then I won't toss it. They are related. If head comes, then I will toss it. If head does not come, then I won't toss it. So they are collinear, they are interrelated. But if I just toss two coins, or if I toss one coin two times, and if I see what is the outcome, then they are related to each. They are not related to each. This is independence in the event. Same thing, if I have three X colors, red, green, and blue, then these three colors are independent to each other. So in the angular domain, if I see red color and blue, then going in one direction would not make any difference in other two directions. Or x-axis, y-axis, and z-axis, if I grow in x-axis, then y and z are there completely unrelated. Okay, like if this is, okay, so I have two pens. So this pen is x-axis, and this pen is another vector. This is x-axis vector, and this is x-axis vector, and this is another vector. Okay. Now, what is if I rotate this vector like this? Its x component is varying. If I do like this, then it has no shadow on the x component. The energy, if this is vector is energy, if vector is energy, then it has direction along y-axis. If it has direction along y-axis, then if someone stands on x-axis, then he does not feel any energy on the x-axis. So this is orthogonal. So if a guy, if energy is flowing in y direction, whatever magnitude it has, a guy is standing on x-axis, he is not getting any energy because of this vector. If this vector is slightly tilted now, then a guy who is standing on x-axis, he is getting some energy essence. Okay, so if if the vectors are orthogonal to each other, x-axis, y-axis, z-axis, then if energy is flowing on any of the axes, then other two axes will not get any essence of the energy. This is orthogonal. Orthogonal is a completely research-based area where we proceed all the calculation through orthogonal. Like we do all the kind of business through rupees in India or dollar globally. So at the end, it sits on rupees or dollar. But if we go beyond, then it sits on silver and gold. Okay, not even rupee and dollar. So if we go even more, that the business is based upon what? The business is based upon gold and silver. Okay, today, in the past also. Probably today or in the past, a dollar would not have existed because USA is a new country. So, in that way, so at the end, on what component we depend upon. So, orthogonal component at the end is the base of everything. So, if it is a vector class, then x, y, z direction is the base of the vector class. Okay, now the question arises that what is multiplication in the vector? Okay, now it is understood that from calculus, from the partial derivative to gradient calculation and so many things, we came to a calculation called chain rule. From chain rule, now we are migrating to orthogonal components. So everything can be can be kind of represented in orthogonal components. If there is a vector, and if I say vector is nothing but 2 comma 3 comma 4, means the vector essence, the vector energy along x direction is 2, y direction is 3, and z direction is 3. It is not summation, I would say. It's a set. It's a set of three values 2, 3, and 4. Then we also call it 2i plus 3j plus 4k. So if there is energy flowing in x along x direction and strength is 2, if energy flowing in y direction, so this is xy plane, this is xy plane, energy flowing in x direction, okay, and strength is 2, energy flowing in y direction, strength is 3, and energy flowing along z direction, strength is 4, then if this energy and this energy, if the three get mixed up, combined, and they move in along one direction, then that energy is a resultant vector. That is 2i plus 3j plus 4k. Or we can say in a set fashion that 2, okay. So in a set fashion, we can say that it is 2, 3, and 4. Okay. So this is a vector. 2, 3, and 4. 2, 3, 4 is a vector, means three vectors 2i, 3j, and 4k. Three vectors they combined and they formed a vector called 2, 3, and 4, or 2i plus 3j plus 4k. So if this is the vector, then its energy component along x-axis is 2, energy component along y-axis is 3, and energy component along z-axis is 4. Okay, so this is a kind of a vector tradition. What is a vector? Vector is nothing but energy which has a direction and which has a magnitude, strength. So if anything which is moving in a direction and it has a strength, then this is a vector. Like we have meteorite, like okay, so there is a meteorite in sky. So there is a a meteorite. Okay, so heli meteorite, it is kind of it it moves from, it goes beyond the Pluto, and then it comes in a kind of uh, in a some in a orthogonal way, at some other way, the way the planet rotates. So if this is sun and these are the planets, then it comes in other trajectory way and it goes along all the crosses, all the planets. So that is helix comet. So we call it comet. Okay. So it is a energy that is moving in a direction, and then if energy has a direction, it becomes a vector. So that is a vector. Now the question arising is, if, okay, so if if this is a if this is a vector called A, if this is a vector called A and this is a vector called B, there are two vectors. The black one is A, the black one is A, and blue one is B. If there are two vectors, then black one is A and blue one is B. Then what is A dot B? Okay, very straightforward question. If there are two vectors, one vector and there is another vector. So if there are two vectors, okay, they have some angle theta in between and they are somewhere in the space, okay, not along x-axis, y-axis, z. They have on xyz, on xyz. If there are two vectors like this, so I am considering a positional vector in the sense that their base is at origin. So if there are two vectors like this is A and this is B. What is A dot B? Okay, so pretty simple question. What is A dot B? Someone would ask, we are talking about vector multiplication. Okay, so how we multiply the vector? How we add the vector? Adding vector is simple. If I want to add two vectors, then we can add its component. How we can multiply two vectors? So in multiplication, there is a grammar. There is a kind of, we can say that there is a type of multiplication. It's called dot product. Multiplication among the vectors can be dot product, cross product. So what is the concept of dot product? What is A dot B? Okay. So question arises is, what is A dot B? If this is the case, then what is A dot B? Anyone would ask, what is dot? Dot means that if I want to do dot product of two vectors, then they must have same direction. Then multiply the magnitude. If one vector has magnitude alpha and another vector has magnitude beta and they are in same direction, then their dot product is alpha into beta. Like work done is force into displacement. If displacement and force, so I want displacement in this direction. This is the force I am applying. So force and displacement are in same direction. So force into displacement is work done. So what is dot product of two vectors? If two vectors are in same direction, if they are in same direction, if two vectors are in same direction, then their the multiplication of their magnitude is the dot product. Okay, so this is the condition I am writing on paper, that if I want to multiply two vector A and B through dot product, dot is a type of product, then if they are in same direction, okay, if their energy is in same direction, then we multiply the magnitude. But certainly they are not in the same direction. Okay, so if black is a vector and blue is a vector, then I want A dot B. Black is A and blue is B. Now how to make both go in same direction? If this is theta angle, then if I say B cos theta, then its energy will get reduced little bit as per the cos theta, but it will come in the same direction. Cos theta is base by hypotenuse. So if If I consider this as hypotenuse and this is the theta, then cos theta equal to base by hypotenuse. The base is cos theta into hypotenuse. If that is true, then if this is the vector, I want, if I say this hypotenuse into cos theta, this is the angle, then it will give the base component. That will be less than the hypotenuse. So the, if vector, if vector b, the b cos theta means the power of b, strength of b, or the kind of the magnitude of b. So if b is alpha I, if b is b1i, b2j, b3k, then b1 square plus b2 square plus b3 square square root. That is the strength of the vector. That is the magnitude of the vector. So magnitude of b cos theta. That will be the b the strength along A. So it will reduce. So if I want to do dot product of two vectors, okay, then one vector. So if someone is standing on vector A, then how much he is getting energy from vector B? If they are orthogonal to each other, then anyone who is standing on A, he is not getting any energy from B because cos 90 is 0. But if there is an angle between it and it is not 90 degree, then anyone who is standing on vector A is getting energy from B. Okay, that is B cos theta. So A's magnitude into B magnitude into cos theta. That is the cross product. Now you have to calculate A's magnitude, you have to calculate B magnitude, then you have to find theta between them, and then you have to calculate cos theta. So let's move to our much awaited orthogonal component. Okay, concept of orthogonal. Mathematics is a science of children. Okay, it's not science of very big people because they think faster way and they think step by step. If you give them step by step they will do. If you are habituated of doing things step by step, then mathematics is the simplest thing that you can do. Okay. Now let's do the dot product through component way. Okay. Now I have I have a vector A and I have a vector B. Okay. Now B has three components. Okay. So I would say the equation of B is B1I plus B2J plus B3K. So three vector B1I, B2J and B3K, three vector they combined and they formed B vector. Means this is the history of the B vector. Three vectors were coming, one in positive x direction had a strength B1, one is positive y direction and a strength B2, one in positive z direction and has strength B3. Then B1 I plus B2j and B3k is the whatever the net vector comes in, that is the B. Okay, if that is true, then if there is a vector called alpha I, there is a vector in positive x direction alpha I. So alpha I means a vector which has a strength of alpha and it has direction of I, x-axis. What is B dot I or I dot B? I mean, what is alpha I dot B or B dot alpha I? So dot product of B vector and alpha vector or dot product of alpha vector and B vector. Now this is B vector. V has three components, one along x-axis, one along y-axis, one is along z-axis. Now another vector we are talking about, it is only along x-axis, that is alpha I. Now these three component dot product means two vector must have same direction. If two vector must have same direction, then we multiply the magnitude and that is dot product of two vectors. Now B is nothing but combination of three vectors B1, B2 and B3. Okay, their magnitude are b1, b2, and b3, and their direction is I, j, and k. Now let's calculate all three vectors component along x-axis. Then we can multiply and add, right? This is what the condition of dot product. Two vectors have same direction. If two vector have same direction, then we can multiply the magnitude. Like we did a dot b, there b, we did b cos theta. If we did b cos theta, b came in the direction of a. Now b cos theta is the new magnitude of b in the direction of a. So b cos theta into a. Those magnitude if we multiply, we get the dot product. Now b has three components: b1, b2, b3. Now b1 component b1 its essence along x-axis multiplied by, so we are talking about a vector that is, I believe, alpha I. So alpha I is a vector. So we want b dot alpha I, b vector dot alpha I. Now is b1, b2, b3. So b1 vector, all three are different vectors. So b is nothing but combination of b1, b2, and b3. All three are different vectors. If all three are different vectors, then b1's essence along I-axis, whatever comes in, we multiply it, keep it. b2's essence along a y-axis, we multiply and keep, because it's a set of three vectors. b3's essence along I-axis, multiply it. Now we get another vector which has three components: b1, okay, into alpha along I-axis, b2 into alpha along I-axis, b3 into alpha along I-axis. So b1's component along I-axis is b1, because b1 is along Y-axis. So b1 into alpha is the, now if b1 and alpha, if they are along the same axis, we can multiply their magnitude, because they are two vectors which are in same direction. So b1 into alpha in I direction. Now b2's essence along I direction into alpha. So b2 is in j direction. It has no essence along alpha. So 0. So 0 into alpha, 0. b3 is along k direction. It has no essence along I axis, 0. So what is b vector dot alpha I? That is b1 into alpha. Okay, now what is b dot alpha I plus beta j plus gamma k? I talked about a vector that is alpha I. I talked about a vector that is beta, that is b. So b dot alpha I is b1 alpha. This is what we calculated. So now what is dot product of a vector b and another vector that is alpha I, beta j, and gamma k? If that is true, then b1, okay. So now b is all three component along x-axis, b is all three component along y-axis, b all three components along z-axis. So we have to multiply separately and then we add it the way we did. Okay. Now b is all component b1, b2, b3 along x-axis. Nothing, only b1 exists. Now b is all component along y-axis, only b2 exists. B is all component along z-axis, only b3 exists. So it will come as b1 alpha is a new vector along x-axis. b2 beta is a new vector along j-axis. b3 into gamma is new vector along k-axis. So if I say b dot alpha I plus beta j plus gamma k vector, then it would come as b1 alpha plus b1 alpha I plus b2 beta j plus b3 gamma k. because all others are 0. If that is true, then dot product of two vectors, if we say component y, it's a simple multiplication of their components, and then we have to create a set or we add it, whatever we do. So if there is a vector called b1 I plus, if there is a vector b which has three components at b1, b2, b3, and there is another vector which has three components as alpha, beta, gamma. If we do dot product, that is nothing but their individual components multiplication. So their three components now are alpha, b1 alpha, b2 gamma, b1 alpha, b2 beta, and b3 gamma. So it will come as three vector, different vector, and if we combine three, that is the resultant of b dot. Now alpha I, beta j, and gamma k, that vector is A. So we started discussion with that what is A dot B. Okay, what is A dot B? Okay, B dot alpha I is nothing but B1 alpha in I direction. Others, B1 alpha plus B2 alpha plus B3 alpha. So B2 alpha and B3 alpha are 0 because I and J they are orthogonal, and I and K are orthogonal. Similarly, B1 dot alpha I plus beta j plus gamma k equal to B1 alpha, B2 alpha, B3 alpha. Okay, one component. Now B1, now B2, now B1 beta, B2 beta, and B3 beta. That is another component. So another vector. It will result in another vector. Third vector, B1 gamma, B2 gamma, B3 gamma. So only B3 gamma would exist. Here B2 beta would exist, where B1 alpha would exist. So dot product of two vectors is nothing but individual components multiplication. Now, alpha, beta, gamma, instead of that, I would say A1, A2, A3. So, A1, A2, A3 are three component of this vector. And B1, B2, B3 are three component of this vector. If I do dot product, it will come as B1, A1 in I direction, B2, A2 in J direction, and B3, A3 in K direction. So, dot product of our two vectors are nothing but simple multiplication of their components, and then we can keep these components. So three components mean three vectors. So if B is combination of B1, B2, B3, three vectors in three directions. A is combination of three vectors A1, A2, A3 in three directions. Then their dot product is three vectors where each vector is A1 into B1. That strength is A1 into B1, moving in I direction, A2 into B2, moving in J direction, A3 into B3, moving into K direction. So if there are three vectors like that, if we sum it, if we combine it, whatever is the resultant vector, that is A dot B. Okay. Now, can you see how simple it is then? Calculating the magnitude of A, calculating the magnitude of B, finding the angle between them, and then anyway, if you calculate the magnitude of A, you need all three components. Magnitude of B, or you need all three components. You have to apply Pythagoras theorem, and then angle you have to find then cos theta. Simple A1 B1 plus A2 B2 plus A3 B3. Okay, so the dot product of two vector, if we want, then one vector ascends along three axes, another vector, okay, another vector, one vector ascends along three axes, another vector ascends along three axes, multiply it, and whatever three values we get, those are the component of the resultant. Okay, so if these are the three components of a particular vector, and these are the three components of another vector, if we want dot product, then green we have to multiply. Whatever comes is the green component. Red we have to multiply. Whatever comes as new another component, and blue we have to multiply whatever comes as another component. So these are three components. Okay, this is story of dot product. We will move on it. So, what example we can see through dot product, that we will see.